So we have this sampling notion of probability. And this is the idea that we can identify the likelihoods of different outcomes by conducting experiments or doing things a lot. And that in the long run, we should see the same results, the same outcomes, as well as the same probabilities as if we had the infinite mental capacity to think about all the possible outcomes. So another benefit of this sampling notion of probability is that in the social sciences, not all of the outcomes that we're interested in are easy to determine all the outcomes for. So we looked at some examples of the policing strategy, the marker experiment, as well as flipping coins. And all of these different experiments, these different activities, had one thing in common. So that one thing was that whenever the experiment or activity was conducted, there were only a finite number of outcomes that it could occur. So with the marker experiment, there were 9 possible outcomes, ranging from -4 to 0 to 4. When it came to flipping the 3 coins, there were 8 different outcomes, and when it came to flipping those coins, we could only see either 0 heads, 1 heads, 2 heads, or 3 heads. So in these experiments and these activities, there was no possibility to see something like 1.5 heads. While there are plenty of real-world situations where we would see things like this, a lot of times the questions we have as social scientists are not so discrete. They're not so categorical, not so qualitative. They tend to be more continuous in nature, more numerical. If you think about the research that you've been conducting in this class, so if I pick on the campus parking survey, one of the questions they asked people were, how long does it take you to find a parking spot on campus? So people could have reported 30 minutes. They could have reported 33 minutes. They could have reported 0 minutes. They could have reported 120 minutes. It's also possible that people could have reported minutes and seconds. So if we were in this situation where we wanted to know, say, the average amount of time that it takes for students to find a parking spot on campus, we're going to get some kind of interval or ratio level type value. And there are going to be a lot of them. And it can be difficult, if not impossible, to not only identify all the possible averages you might see, but it might be also difficult, if not impossible, to think about all the different probabilities associated with those outcomes. So one of the other benefits of the sampling notion of probability is that it allows us to look at more continuous type outcomes. So another way that this sampling notion of probability is effective is for asking questions about the average amount of time it takes for someone to find a parking spot on campus. So we have this notion of the sampling distribution of a sample statistic. So this again is a probability distribution. It's a probability distribution for a sample statistic, such as a mean or a proportion. And it's developed by drawing a very large number of samples of the same size from some population. by working in this fashion, we can ask questions such as, what is the probability of, say, inmates on average reporting that they've been involved with the prison system for 120 months or more? We can also think about this in terms of your own research. So if we pick on the Health and Wellness Survey, we know that there's a population of students on campus. We can go out and take a random sample of students. We can then ask them how much sleep they get per night. We can then calculate an average, say the sample mean. We could then go out and do this activity another time. Collect another random sample, calculate another sample mean. Now, if we continued this process again and again and again, then we're going to end up with a lot of sample means, which we then can use to determine our sampling distribution, or the probability distribution for this continuous outcome. So here I want to give you more of a visual representation of what I'm talking about. So here we have this big circle full of tiny dots. This is our visual representation of a population. We then have a much smaller circle, which has its own collection of tiny dots. This represents a random sample. So here, let's pretend that it's a random sample of, say, 50 analytical units. Now for the population, we know there are certain characteristics about it. We know that for whatever we're interested in measuring, there's going to be some mean value, often represented by mu, as well as some standard deviation, represented by sigma. When it comes to the sample, however, we don't talk about things in terms of population parameters. Instead, we talk about things in terms of sample statistics. So the sample mean is represented by an X with a bar over it, and the standard deviation for the values that we measured from the analytical units in this sample, we represent with this lowercase s. So we can think about this in terms of the prison climate survey. So here, let's imagine that this population represents a population of inmates. So there are 3,516 inmates in the population of inmates. What we could do is we could go out and we could take a random sample of 50 inmates from this population, and then based off of that sample of 50 inmates, we could ask them how many months they've been involved in the system, and based off of all those responses, we could then calculate a sample mean. In this case, we've got a sample mean of 98.08 months. So we could go out and we can repeat that exercise. So we could go back to the population, take another random sample, ask everybody how many months they've been involved in the system, take those 50 responses, and then calculate another sample mean. So we might get something like 80.3 months. We could then continue doing this activity again and again and again until we've taken, say, 32 random samples of size 50 from the population. And for each one of these samples, we could ask the inmates how many months they've been involved, and then from those responses, we can calculate the sample mean for each one of those random samples. And we can keep doing this. maybe we decide to do this 288 times. So imagine that we did this. Imagine that we had this population of inmates, and we took 288 random samples, each of size 50. And for each one of these random samples, we calculated a sample mean. So now we have 288 sample means. So now we can treat all of these sample means like they're data. So if you look on the left, this is a histogram of those 288 sample means. Each of those sample means involved sampling 50 inmates. And in addition to constructing a histogram, we could also calculate the mean of those sample means. In this case, it turns out to be 95.61 months. If we continue this process of drawing samples from the population and calculating sample means, let's say we did it 100,000 times, then we'd have 100,000 sample means, which we could then plot using a histogram, and we get this graphic to the right. We could also calculate the mean of those means, which in this case, it comes out to be 95.89. One of the things we notice is that when taking random samples from a population repeatedly, that the distribution of, say, the sample mean calculated for those samples will have a normal distribution. That most of the values will be clustered around the mean of means, so the center, and that as we go out to the lower or the upper tail, we'll see that the number of sample means that fall into those regions will tend to taper off. And we see that this normal distribution becomes more normal looking the more random samples we take. So if we go to the inmate population and we just keep taking random samples, we keep calculating these sample means, and we did this forever, then the histogram we see on the right would continue to take on that bell-shaped appearance. And it would continue to go in this direction until it is so perfect that our eyeballs literally cannot see any jagged marks around the edges, until it looked perfectly smooth. So think of it similar to the situation of flipping a coin through the virtual coin toss. If we repeated the experiment, if we repeated the exercise, the activity, again and again and again, millions of times, millions of times, then eventually we'll, one, identify all the different outcomes, and two, get a probability distribution that is consistent with the probability distribution we could have had if it was humanly possible to think about all the possible outcomes. And of course, like with flipping coins, or the marker experiment, or the policing experiment, there are benefits to knowing about a probability distribution. So based on the probability distributions that we have right here, we could start asking questions like, what is the probability that the average months involved among inmates would equal 120 or more? If we look at this histogram, we can see that 120 is more out toward the tails, So 120 or more is a small proportion of that entire picture. So we see that it would be unlikely. We could also ask questions about, say, the probability of taking a random sample and having those inmates have a mean months involved of, say, 160 months or more. So we can look at 160 months on that x-axis, and we can see that it's so rare that it almost looks like it's flat. So probability distributions allow us to have these kinds of conversations. They let us ask these kinds of questions. And when it comes to things such as sample means, which we often care about as social scientists, we can construct probability distributions once we start thinking about things over the long run. So there's a really famous result called the central limit theorem. So the central limit theorem states that if we focus on large samples and their statistics, say sample means over the long run, then we can identify the probability distribution, and that distribution will always be normally distributed. So imagine you have some population, all students on campus. Take a random sample of students. You calculate a sample mean. You do it again and again and again, forever. The central limit theorem tells us that if your sample size was large, say equal to 30 or more, then this activity will yield a probability distribution, and that this probability distribution will be normally distributed, always. So again, you can kind of see this. As we continue to take more random samples, the distribution of those sample means that we get tends to better approximate that normal distribution. And this holds regardless of the distribution of the original population in which you're sampling from. So on the right is the population of inmates. So we have these 3,516 inmates. And we asked each one of these inmates, how long have you been involved in the prison system? If we took all of those values and plotted them on a histogram, we get this right-skewed distribution. That's what's happening in the original population. But if we go out to that population and we take a random sample, here of size 50, we calculate the mean number of months that the inmates have been involved, and we do that again and again and again, then the distribution of those sample means will be normally distributed. And this holds true regardless of whether we're talking about inmates or we're talking about how long it takes you to find parking on campus. Another fact that is worth pointing out is that the mean of the sample means is very close to the mean in the original population. And in fact, if we were to continue to take random samples, and if we did this forever, then the mean of those means would converge and eventually equal the mean in the original population. More formally, this is what the sampling distribution of, say, the sample mean looks like. It has that bell-shaped curve. most of the means that you're going to see are going to fall in the center. Means that are really small are going to be out more toward the tails. Means that are increasingly large are going to be out toward the upper tail. The mean of the sampling distribution of the sample mean equals mu, and the standard deviation of the sampling distribution of the sample mean equals sigma over the square root of n. So this expression, sigma over the square root of n, is referred to as the standard error of the mean. And I want to point out that when it comes to the sampling distribution of the sample mean, its mean is equal to the mean in the original population. And its standard deviation is equal to the standard deviation in the original population divided by the square root of the sample size. Okay, so what do sampling distributions and the central limit theorem let us do? So these results allow us to ask probabilistic questions about sample statistics, so means and proportions. In the context of the Prison Climate Survey, we can ask things like, what is the probability of seeing a sample mean of 180 months or more over the long run? So remember, it's that over the long run that allows us to construct the sampling distribution, which is another term for probability distribution. These results also let us ask questions such as, what is the sample mean associated with the upper 0.05 probability of the sample distribution over the long run? So think back to the policing experiment. So if you recall, the probability distribution ranged from -4 to 4, and that it was highly unlikely to observe results according to that distribution if they were out toward the tails, if they equaled a 3 or a 4 or a -3 or a -4. So based on these results, this allows us to do kind of that same thing when working with more continuous outcomes, say the mean of a random sample. Okay, so we'll start exploring these ideas starting Thursday and as well just throughout the semester. So in summary, we talked about the sampling notion of probability, the sampling distribution for the sample mean, as well as the central limit theorem.